Okay, well, nothing like starting a live stream already torqued off at technology this morning. Definitely getting under my skin here. I don't know what was going on, but anyways, well, this is Mark, KA6WKE, and I'm starting, well, this is formerly known as, how should I say, as KA6WKE live stream, and I'm your virtual Elmer, but this has changed. And so what brought this on, I actually changed the name to bench therapy. Kind of a, let's see, got my audio a little hot here. Let's see, let me turn this down just a hair. Okay, so bench therapy. So how did I come up with that name? It's something I've used with my wife. You know, I have a stressful day at work, and I say I just need some bench therapy. Go melt some solder for an hour or so. While she watches one of her shows I don't care for, and been doing this for a couple of years. And then I came up with the idea, I really like to live stream what I'm doing, what I'm building, and things like that. And I don't know what's going on with YouTube because I cannot tell if I'm actually live streaming. Let's see, a refresh on the screen here. Play. Ah, I am live. Okay. Yeah, my little monitor here was still showing the default screen. So anyways, it's something I like to do, and it's what I call bench therapy. And she knows sometimes when I'm grumpy or whatever, she'll say, "You need some bench therapy. Get out of here." So I decided to change the name from KA6WKE live stream, although technically correct, not very memorable. I switched it to bench therapy, and those were brought on a lot by changes in the name. Also brought on by making changes in the audio quality, which after watching last month's live stream was, although my voice was there, if you turned the volume way up, I spent a lot more time working on getting better quality video, and I hope it's apparent today that you can actually hear me at normal volumes. And the other thing is, I finally had to make a decision on the quality of the videos. So watching last month's video on the Arizona QRP antenna analyzer build, I just had to finally make a decision. Am I going to be serious about this and actually produce a high quality stream? I really enjoy doing this. It's a lot of fun, and I just had to come to that conclusion. If I'm going to do this right, I need higher quality video equipment and audio quality and everything to make a live stream. It's just not as simple as throwing up a webcam and talking about what you're passionate about. It's also the quality of what you're doing, not just the electronics work, but also the quality of the video that you're watching right now. So with that said, I had went through and spent another trip around the sun last month in April, and I convinced myself that I really need a high quality video capture and scope system to show what I'm working on. So I invested in an AM scope. It's an SM3-3TP scope. It'll go up to 90 times zoom, and it's a trinocular system with simul focus, which means the camera part that's sticking above captures what I see through the left eyepiece. So some scopes you have to pay attention to is some scopes will lose the left eye. There's a little lever on the side of the scope to switch it to camera. And I didn't want to do that because the benefits of having a binocular scope is actually having a three-dimensional view of what you're working on. And this is an HDMI camera on top that runs into a small capture card, HDMI capture card that open broadcast software can work with. So what this means is I can actually stream at 1080p, 60 frames a second. So there's no blur, there's no motion blur in the video, and I've just been practicing with it with the last month, and it's been just pretty much amazing with the quality of work that I've been able to do this past month on some of the other projects. One of them was reviewing the Arizona QRP analyzer, the work I did there, and most of it was really good. I did that as a separate video that I'll post later, probably middle of the week. That was my first attempt with the scope. Done a lot of practice this month with it. Having an entirely different view of your project takes a little getting used to, but I think you'll really enjoy it. So for this month, I started working on 4 or 5 years ago, maybe 6 now, on a vector network analyzer that was originally designed by N2PK, and I wanted a nice piece of test equipment that I could use, obviously, for my projects. And I knew I really wanted one, a vector network analyzer, but the problem with that is they are normally very expensive. So I found this kit, and after reading it, I should say this project, it's really not a kit per se, because you can order the boards and all that, and then you have to order all the parts on your own, of which I have an updated spreadsheet that I could post. I'll have to find it with DigiKey parts on it, and I could post that in the show notes below. So I started building this, like I said, more off than on over the years, and it's completed, but it needs the final inspection to make sure all the solder joints are good and things like that, and we'll go through that today. Let me minimize the OBS real quick here and switch the scene. All right. Okay. We'll go quickly over the website, and there we go. So you can see my open broadcast software in here. So this is the website for the project. There's actually 2 of them. Makarov has the entire project documentation on his website. You can also go to N2PK itself, N2PK.com, on Paul's website, to read about the history of how he designed this and how it functions internally. Be aware there's some math involved, which I have to review. I don't. It's been a long time since I've done engineering mathematics, so you can get more information about how we developed the parallel port version. N2PK now uses USB, so let's see. We can take a look at some assembled boards. There's a lot of information here that's helpful in building the board. This is not the current board. This is, I think, for the parallel port version. There's not a whole lot of parts. There's not, this is the older design. There's not a whole lot of parts. They're spread out pretty well. I was able to hand solder this. This is before I had a hot air workstation. I was able to hand solder this on my own with just wearing one of those visors with magnifiers built in. And I gotta learn to stop saying so much. So I'll put Makarov's website in the notes below. But for right now, back to bench. I thought I had a photos of my work. But anyways, we'll get started with the board today. So this is it. Well, this is the, oops. You get to see sort of what I look like. Hold on a second. There we go. All right, back to the scope. Oh, I gotta turn things on. Get things turned on here. Where's my distilled water for my sponge? I like distilled water on my sponges so it doesn't get any of that hard water stuff in it. So now this is the quality of video that I'm able to do with this scope and the capture card. And we'll get started with the overview of the schematic. Let's go back to screen real quick, just to describe in high-level terms how a vector network analyzer works. So you're asking yourself probably, what is a VNA and what is it good for? So let's back up a little bit and talk about some simpler pieces of test equipment called a scalar network analyzer. And I'm sure we're all pretty familiar with a spectrum analyzer and how it displays the magnitude of the frequency over a certain bandwidth. And for example, like if you're going to be looking at a low pass filter, starting on the left side, the magnitude of the signal is going to be higher. And then as you start to get into the cutoff frequency for your low pass filter, the amplitude of those signals start to drop off. Maybe they drop off in a straight line, maybe they don't, they got little bumps and things. So that's a scalar network analyzer where it just shows magnitude and frequency. So another use for, well, another piece of test equipment that a lot of us probably already have is a regular antenna analyzer. So how does that work? Well, inside an antenna analyzer, if you're not familiar, there's a frequency source, and then there's an SWR bridge inside, and with the appropriate measurement components surrounding that, it can take SWR measurements. And when they first came out, that's all they could do is have, to show you the SWR. But as time progressed, they added more capabilities where they can actually measure the resistance as a magnitude of the antenna. So everything in the amateur radio world, almost everything in the amateur radio world, is 50 ohms resistance, or I should say impedance. So with 50 ohms impedance, that means there's 50 ohm resistance plus no reactance, either capacitive or inductive reactance. But some of the antenna analyzers, they can give you a number for the reactance, but you'll notice on the most common ones, you don't get the sign of if it's capacitive reactance or inductive reactance especially for a single frequency. So, for example, the equation for this would be fire up. I have Notepad handy. I guess I don't. Notepad. There we go. So for example, the antenna analyzer might show a resistance equal 50 ohms, and I can't write a lowercase s on this, x sub s of 0 ohms. So that would be resonance for, say, a particular antenna. But sometimes you might see something like this, 23. So x sub s for your reactance equals 27, say. It'll give you this. But the problem is you can't, by looking at this, the problem is you can't tell if it's inductive reactance or capacitive reactance because there's no sign. The equation simply looks like this. A resistance can be plus, on fat fingers, plus or minus I, and then we'll just call it y for now. Z, there we go. In that form, so it can be resistance plus or minus some imaginary number, and that imaginary number is the reactance. But the typical, popular antenna analyzers can't determine these signs. So, but you can kind of, there's actually a workaround for it. If you want to know if this sign's negative or capacitive reactance or inductive reactance, first off, the resistance and the reactance are all just simple algebraic equations that can be solved, and you can give you this number at the top, or value at the top, I should say. And in order to determine if it's capacitive reactance or inductive reactance, you can first, you want to find resonance, which would be R equals 50 and x sub s for the reactance equals 0. So when that match, or when that reading occurs, that's resonance for your antenna. But to determine if something is, say, capacitive or not, if you increase the frequency and this number increases with it, that's inductive reactance, so you know your sign's a positive. If it decreases as you start from 0 and say it decreases to minus 15, then it's capacitive. So that's how you can kind of infer your way to what if the reading has capacitive or inductive reactance in it. So that's really about the best way I can do it without digging into some math on imaginary numbers and things, which I'm very, very out of practice with. So I'm sure all the professional engineers are going there, but you forgot this, and yeah, probably did. So, but hopefully I communicated what's communicated well enough that you understand this concept. So what a vector network analyzer does, it will give you that sign at a single frequency. Because not only does it measure the magnitude of the resistance, for example, it also measures the phase angle of the return RF signal coming back into the detectors, and we'll go over this here in a minute on a big scale. I have not gone over or dug into details on all the chips and things on what they do. I do it at a high level, but I haven't read all the data sheets and things like that in a number of years. So we will just get started on the signal flow and what's going on with a vector network analyzer, specifically this one here. But they all work in the same fashion. They just have higher or expensive components, higher tolerance components inside, lots of testing, lots of certifications. You know, you can get National Institute of Standards and Technology, NIST certifications for your equipment and things like that, and that's what makes things very expensive. But for the hobbyist or amateur radio use, we don't necessarily need that. Good enough is a term that I like to put around, that I like to say, so you can, you don't have to have this expensive equipment or have to purchase this expensive equipment. You can actually build something very nice, accurate enough for hobbyist work, and learn something along the way about how these vector network analyzers work. The good news is, if all of that what I've been talking about so far just went in one ear and out the other, and you're ready to shut down and stop watching this, I'd appreciate if you just hang on for a little bit longer. Because the good news is, you don't have to know all the stuff that I just talked about. You just need to know how to read a schematic, read part numbers, and know where they go on the board and solder them down. That's all you really need to do. You don't have to understand a theory of how they work. You can still enjoy a project and build it and have a nice piece of test equipment or a radio or whatever accessory you're building without having extensive electronics knowledge. Let's see. So let's get started with the N2PK. So this this big chip here, this is for the USB port. So it has its support. It has its crystal oscillator here. It's got its voltage regulator here for 3.3 volts. And a little bit of memory down here. I think it's 64 kilobytes for storing probably parameters of some kind for the operation of the VNA. I'm not exactly sure what's stored there off the top of my head. So it takes a signal from the computer, from the software, and the software that seems to be most popular is called VNWA, and I'll put that in the description below the video when I post it. And converts it to a signal that these two chips here, the 809851s, can use. So these two chips are kind of the heart. They are the heart of the system. These are essentially digitally controlled little transmitters from 0.5 to roughly 60 megahertz. And they emit, they can create an RF signal anywhere between there at a given amplitude. And I'm pretty sure you can also do different phase angles. I'm not positive on that. Again, have to pull down the data sheet to take a look. So then the output signal, whatever has been programmed by the software, comes through the USB, through some, these are probably just some buffering type chip here, and tells it to go on, let's say 10 megahertz. So the signal here is 10 megahertz, and it goes through a little impedance and matching transformer, then out through a filter network to clean things up. So you can have, as pure as possible, a 10 megahertz signal and none of the harmonics and things like that, or other noise. This one, so this is the main RF output. This one here it does the same thing, except it has two outputs, one for each of the detectors. And what do the detectors do? Well, they detect. They detect the signal coming back from your what's called a device under test. Sometimes you'll see it as DUT. And from there, the numbers are crunched. It takes the readings, numbers are crunched, and are displayed back in the software, the VNWA software. So you can get measurements like this. So for example, here's a bandpass filter. Again, this can also be done with a scalar network analyzer or a spectrum analyzer. And we can see the shape of the filter and its little lobes that are hanging out around here. So it's not a perfect, it's not a perfect curve here. It's got little bumps and things in it. Here is looking at the output of a crystal resonator transmission test. And I'm not exactly sure what this means, but degrees. This is measuring, I'd say, the phase angle of all this. So we've got so we got the slope here of the gain, and then 15 degrees per division of the, I want to say, the phase angle. That you cannot do with your typical antenna analyzer. Of course, you can do Smith chart. Well, and that's all done in the software for you. The hardware part of all this just brings in all the processing. So the software does all the number crunching for you, creates the graphs and things like that. So okay, that's about the highest level overview of a vector network analyzer I can think of, and I hope that's sufficient to why this is a nice tool to have. But you can also use it for other things. You can use it as a signal generator if you just need, 10 megahertz for something at a specific magnitude, a specific output, dBm, for example. So there are other uses for this that make it a really handy piece of test equipment. And I think, if I remember correctly, with the board and this, and I don't have the case yet or the power supply I need for it, I think I invested about $300 total. So that's really, I believe, a great cost for a very nice piece of test equipment that you get to build. And the building helps you understand all the major blocks of all the circuits and things. So when something goes wrong, you have a good chance of actually fixing it. So we'll get started looking at the board. And that's the USB chip. And this was all soldered by hand. I did not use a hot air workstation on it. And I'm really surprised at how well it came out. You see these little solder balls around here? That's from the paste I used. But then I stopped using paste. I went on to use something. I ended up using regular solder. And while I still practice with this, the field of view that I have inside the microscope is a little different than what you're seeing on the screen. Let's see if I can kind of get this to focus a little better. Okay. Some light adjustment, see if this helps. Okay. So again, this is all soldered by hand. I used +3 diopter, those little cheater reading glasses you can get from the pharmacy or Target or wherever. At the time, I started doing this, I did not have presbyopia, which is what affects people as they age. And so I don't think I did too bad of a job. There's some cleanup we can do here. This chip's looking good. just touch up a few things here. Like it's soldered down. Okay. Clean it up in a this end didn't come out very well. So this is the way I originally soldered it down, was just by doing this. Drag soldering, as it's called. And then using solder wick, which I just now have run out. I will have to get more. Go through and just wick up the extra. Jason's around. I gotta figure out a way to hold these things down. All right. That looks a lot better. Okay, we'll check this one here. It looks like I got a bridge. It may be allowed here. It may be part of the design, I don't know. It does look like that, doesn't it? Okay, we'll leave that alone. Actually, we're not. Let's see. Some flux on here, so we can start. Here we go. Some flux down, and we will reheat all of that. Now remember, when you're starting to heat up, starting to work on a board, you want to gently warm the area up. All right, that looks better. Now we'll move up to the next chip up here, which is the, so the one chip I just reflowed, that's U110. That's the little transmitter chip that is controlled by the USB chip down here. And so this one up here is its brother, could be sister, I guess. That doesn't look too bad. All right. One's a little off. This is the memory chip. A little bit of memory in there, and we will flow that one too. I don't think it's all on the pads on the right side. It's there. Oops. Come on. Even had decaf this morning. What's going on? There we go. Okay, that's better. Okay. So this is the main oscillator. And looking at that, other than it's got a lot of solder balls down there. Going to reheat that one, but not with hot air. All right. These are the inductors for the filtering that was in the schematic. Same here. Those look okay. Crooked resistors are fine. Upside down resistors. I need to change that around. I think it doesn't that change the electron flow or something? Yeah, just kidding. So as far as the output transformer for the local oscillator output, the main RF signal. Okay, ferrite beads. Does that hurt? I don't recognize. Okay, related to the USB, so I want to look underneath it. I'm not sure what's going on with this. I'm still getting used to this, how to look through the scope. Still trying to find the best distance from okay. Get these pads cleaned up. Get all the burned up solder removed. And this is just plain, well, not plain old. It is it's 100% denatured alcohol. It's not the stuff you get at the grocery store or your pharmacy where it's 70% or 80%, because that 10% that it's not is water. I don't like the idea of putting water on my projects. Bath when I'm done here. Don't scrape, keep turning. Put some solder down on there. Let's first more flux. Excuse me. Or okay. Or clean flux off that too. Go through a lot of Q-tips on some of these projects, that's for sure. Let's see. Try not to area too sticky. funny to watch the delay in the monitor from YouTube. Really tight on the pads there. Okay. Boy, this one doesn't want to solder down at all. All right, no heat. Switch to flip hands. There it goes. Check the other side. All right. Let's take a look at this on the edge here. A little fuzzy. Quite raise the scope any higher. But it looks like flowed nicely. Okay. The parts we got here. Here, part is. Doesn't look like that lower right pin is soldered down to anything. Not be fully soldered on that. A bridge right there to take care of. There we go. That's better. Okay. Way around the board. Now we'll be looking at the first detector. This one. Okay, the one above it doesn't look like it has enough solder on it. How are we doing on time here? Oh, it's already been an hour. Okay. Cool. Last time. So this technique here that I'm using by hand, and this is the way I soldered the vast majority of this. A lot of it came out really good. So okay, not even soldered down on that one. Can't solder with solder weight. There we go. That one is a little off center. I think that one too. Flux is your friend when you're doing work like this. Oh, wrong one. It's okay if some of the other parts reflow around it. There we are. See how that just snapped right into place due to the surface tension of the solder? All right, that's better. Oh, this one here, look at that. Same technique. All right. It's not too bad. We can just touch that up with the iron. Not more than I anticipated. That's okay. I originally soldered all this stuff down. I started stuffing the board. Did not use flux I am using today. I used whatever was in solder itself. Now I'm seeing why solder I'm using, the this. The Amtech NC559 V2TF. There we go. That's what I'm using for, it looks huge in the camera. With the lowest magnification I can go. So this is what I use today on the board. Okay, so we got this nicely cleaned up. Also, a couple of them are a little low. There we go. So we can see a few of them are solder joints. they're okay. Some need to be touched up, but so we'll. Okay, that's my. All right, it's detector 1. So when you're building a kit, well, a project that doesn't really have instructions on how to do this, step by step, put resistor 1 here, etc., etc. What I like to do is to put everything down that generates the power rails. So this one has 12 volts, 5 volts, 3.3, and minus 5, if I remember correctly. And I build those up. I build those up first, and then test them. Make sure I'm getting the right voltages. It makes it a lot easier to know your power rails are good when you start testing the rest of it. All right, so let's look at this. Detector 2. Oh, this part was done with the solder paste. I like it. Solder paste coming out of syringe. I think that's the problem. It's difficult to apply the right amount. You either get too much or not enough. Here, clearly doesn't have enough solder on it. What is that? A hole. Huh. That was. Yeah, we'll fix that. Solder. I think if you use solder paste and stencils, it would probably be able to apply the correct amount. Weird. Drag solder along here. Well, up our bridges. Okay. Turn this around because it's kind of falling off the bench. Tighten it up, 2440. resistor right here. Okay, not down. Solder around it. These need to be touched up too. Let's do it. Same. Got a solder ball over there. Okay. Oh, now that's nasty. That. I still got to practice on my focusing because it looks. See, that's pretty bad. Don't know what I was doing there. We're just going to take that off. Clean the board up. Looks like I'm putting 5 gallons of alcohol down here, but really the lowest magnification of the scope. Solder back down on the pads. And this is the technique I've been starting to use more often instead of using solder paste. Solder paste would be great if I had stencils, sure. Too much solder down. Let's take a look at the chip. Okay. Where'd you go? Pay attention to the orientation. Off the mark. Get it close enough and start to read. I know what the problem is. It's giving me some flux down. That'll help hold it. Okay. Okay. That is a lot better. Don't know what the problem was. What happened to it? Poor thing. Deserve a better solder job than that. Touch up with the iron. Okay. He is a happy camper. Pretty sure it's a he. Got some additional away here. Notice I can move things around and the board isn't smudging or smearing, I think is the right word. I have to practice focusing. That'll work. I'll get better at it as time goes by. Touch that up with the iron. Okay. And its neighbor. Okay. Else that looks too right. Okay. Cap zapper touched up. See, when you don't have a decent amount of flux on the parts, solder just doesn't want to go anywhere. It shouldn't. Smoke. Solder smoke. You can see all the solder balls around this one here. Let's take a closer look. See all the solder balls around there. Just kind of keep diving in. On that capacitor. See, there's all kinds of solder balls around. So I'm off the center. Sorry about that. Okay. That's better. A little out of focus still. Clean that up nicely. Back out of this. Whoops, sorry about that. Right. Backside. That's all we have left. Okay. Dial this back out again. That 24 megahertz crystal that was for the USB chip. There it is. Oops, sorry about that. I bumped it. That. Right. Actually, it looks good on the left. Touch up. C connector. $24.9. It's got enough solder on the one end. A little more difficult when you've got all the connectors in place and all that. It's okay. Everything flows better with flux. Cap zapiters, fine. Look at that. One with another hole in it. Jeez. C281 doesn't have solder on the side. Okay. Done. Be the same way. Flows better with flux. Okay. Last section. Same to these three. Watching on the second monitor, the lack of motion blur. Touch this one up because it's got a lot of solder balls around it. That's it. That's it for this board. Okay. So that takes care of cleaning that board up so it's ready to be tested. Let's do that actually. I don't have an overhead camera. Let's check to see if I have any. Do a quick continuity check to make sure that I don't have any shorts or anything on the power rails. So we'll search for them on the my DMM in diode mode. Take a look. So we've got ground right here. There. Got +5 up here. Okay, didn't tone. Where to? Okay. What else do we have? Voltage pad poking out there. Ground. I think that's ground. It's another voltage. Diode mode showing 1316. That's okay. 2.5 volt rail. Okay. Looks like I'm missing something right here. C261. On detector 1. That's interesting. That happened. Get a quick note of this. Okay. Okay, there's +5 and -5. There. Let's check the second one. Same 5 good. All right. 5 is good. -11. Good. Gotta check the other one. That's the one that's missing. There. Ground. Yep. It is. Check. Okay. Well, no shorts on the rails, so that's good. That means you can probably safely power it up, apply power to it, and see if it retains all of its magic smoke. And that's all I have for today. I hope you enjoyed it. Hope you enjoyed the better quality audio and video. Still need some practice with the scope. Got to learn how to keep things correctly focused and centered, since the view that I have through the camera is entirely different. Well, not entirely different, but it's smaller than what I see through the eyepieces. Okay. Here's the project you may want to tackle. N2PK Vector Network Analyzer. So for next month, I'm planning on working on a top view camera, so you can actually see my entire work area outside of the scope. So that way I can continue building the projects as an entire project, not simply soldering components down on a board and getting things done. So I've got 2 of the projects I need to finish. The Arizona QRP one I need to finish because I'm desperate for an antenna analyzer that's portable. I've got this N2PK VNA that I want to finish just because I've had it for so long. I want to get that wrapped up. So for both of them, for both projects, I need power supply. The Arizona QRP one's going to have lithium rechargeables in it. And this one is going to need its own plus 12 and I think just plus 12 volts for it. I'll have to double check, but it's going to need its own high quality power supply. No switch mode power supplies or anything. I don't want to risk any noise getting in there. I may just design my own. I'm giving it a lot of thought. I'm just going to design my own and actually design it. I'll have the PCB available for download from my Git repository. It'll be done in KiCad. And once that part's done, I can actually get a case for this and start turning it into a proper project. Same with the Arizona one. So with that, I hope you enjoyed what went on today and you learned something. So for this stream, I'm going to say 7.3. I have to go fix our ice maker in our freezer. So I will catch you on the first Saturday of next month, next June. I don't know what date that is, but this live stream is on the first Saturday of every month at 10:30 a.m. Eastern. It's 10:30 a.m. Pacific, 2:30 Eastern, and I don't remember what it is in UTC. I think it's 1800. So 7.3. Find a project you want to build and log about it. Write it up. Talk to you later.